good morning, good afternoon, wherever you are. My name is Tim McCarthy. I'm the training manager for the Microsemi Programmable Solutions Business Unit, and we're going to be talking about our latest tool suite to support our latest FPGA family, PolarFire. I'm going to give you a quick overview of PolarFire, in case you haven't heard of those exciting products. And then we're going to focus on the tool set that you would use to design with PolarFire, which is called Libero SoC PolarFire. We'll talk about the design flow and the different steps that are included in the tool set to take you all the way from design entry to programming. And then we're going to talk about some exciting debug capabilities that we have that allow you to easily debug your design after you've completed the design entry and programmed the device. So let's start out with taking a look at the broad range of FPGAs that Microsemi provides. We have three different families shown here. They're all reprogrammable devices and are all non-volatile devices, meaning that you don't have to reprogram them every single time you power up the device. The first column here shows the SmartFusion ProASIC 3 and Igloo devices. These are low-density CPLD replacement devices that run in the range of between 100 and 30,000 logic elements. Small devices that you could use to replace traditional CPLDs. Again, these devices are reprogrammable, but they're also non-volatile, so it gives you a little bit of an advantage in terms of security and power. The SmartFusion family has a hard 100 megahertz ARM Cortex-M3, as well as analog blocks, up to 3 A to D converters and up to 3 D to A converters. Moving up to the second column, here we have the SmartFusion 2 and Igloo 2 families. These are low-density FPGAs that range from 5,000 to 150,000 logic elements. And here we've added some other features we never had in the SmartFusion ProASIC 3 Igloo families, like DDR controllers that will support DDR3 memories up to 667 megabits per second. We have SerDes that are capable of 5 gigabit per second operation. And in the SmartFusion 2 family, we have a hard ARM Cortex-M3 processor that runs at 166 megahertz. And then finally, the right column here, our newest family, PolarFire. PolarFire is a mid-range density FPGA that's cost optimized and offers you the lowest power. And we have densities ranging between 100,000 logic elements and 500,000 logic elements, with transceivers that will run up to 12.7 gigabits per second, and IOs that can run at 1.6 gigabits per second for DDR4 or LVDS operation. PolarFire offers you the lowest power, the lowest cost 10 gig SerDes-based FPGA, low cost DDR4 and high speed IO solutions. The smallest form factors, we have packages that are 11 by 11, 11 by 14 and a half, and 16 by 16. We have an SEU immune FPGA fabric, meaning that our interconnect is not disturbed by any type of particles, that sort of thing. Because it's a flash-based technology, there's no configuration chip required, and we have the highest security that's available of any FPGA. And these devices are suitable for use in communications applications, defense and aviation, and industrial applications. So moving on from the devices, now I want to take a look at what the seminar is really can be focused on, which is the software development tool set to allow you to design with the PolarFire device family. So Libero SoC PolarFire is a comprehensive industry standard tool set that takes you all the way from design entry through debug, using tools developed by Microsemi, as well as some popular third-party tools for synthesis and simulation. Libero SoC PolarFire is easy to learn. It has an intuitive design flow, and we have GUI wizards that will guide you through the design process, and it's easy to adopt. We have a single-click flow, so you can create your design and then constrain it and click one button. It will take you all the way through synthesis to programming file generation. We have a rich IP library of cores that you can use when you're implementing your design. We also have the availability of reference designs and development kits. So if you're new to Microsemi's FPGAs and you're interested in PolarFire and you take a look at Libero SoC, it should be very easy for you to get up and running. If you've used some of the earlier families, SmartFusion or SmartFusion 2 or Igloo 2, those were supported by Libero SoC. So the tool you're going to see today looks very similar, but we've made some exciting changes, and I'm going to go over some of those here in a little bit. Now this shows the Libero SoC PolarFire design flow. First, we're going to start out, we're going to create our design. And Libero SoC PolarFire gives you a couple of different options in order to implement your design. And once you've implemented your design, you can simulate it to make sure that it's functionally correct. After you've done that, we move into the implementation stage where we're going to synthesize the design. We're going to run layout. We're going to verify the timing. So in this area, we need constraints. We can generate timing constraints for synthesis, for place and route, and also for timing verification. And there's also other type of constraint files we can use through these different steps. Netlist attribute constraints for synthesis, physical constraints for layout that might include floor planning or pin assignments or I/O attributes. So in Libero SoC PolarFire, we have a constraint manager that allows you to create and manage all of your constraints for all of the design implementation steps. And as you go through and go through some of the implementation steps, like synthesis, for example, you can actually run a post-synthesis simulation. Same thing after layout, you can export your delay information in an SDF timing format file, and you could run a post-layout simulation in addition to running the static timing analysis tools. And once you've gotten through your implementation phase and you've met your timing and optionally your power objectives, then you can move on to programming and debugging, where you generate your bit stream. Then you can hand off the design for production. If you have a processor in a design, you can hand off the design for firmware development, and you can also export files that can be used to debug the design in the lab environment. So this slide shows the different tools and features that are included in Libero SoC PolarFire as you go through the design flow. So we start out with design entry, and with design entry, we have a tool called SmartDesign that I'll introduce you to that allows you to stitch blocks together, or you could use a traditional HDL flow and use Verilog or VHDL to implement your design. You can also use the IP catalog that has IP cores included, and you can implement those as you build your design. When we get to verification, we can simulate our design to make sure it's functionally correct. Libero SoC PolarFire includes the ModelSim Pro ME simulator from Intergraphics. The next step would be to go off and to synthesize the design, take the RTL description, turn it into a netlist that's suitable for the PolarFire family. And here we use the Synopsys Simplify Pro Microsemi edition, or the ME tool. After synthesis, we have a netlist that's going to go into place and route. And from here, all of the tools are Microsemi developed tools. We have a place and route engine that allows us to optimize the layout for timing or power. We have tools that allow us to do chip planning. And then we can move on to timing and power analysis using our Smart Time and Smart Power tools. And then finally, we provide the programming files and the programming tools so that you can program the devices. And then we can move on to the debugging stage, and we can take advantage of a Microsemi tool that I'll introduce you to that's called SmartDebug. And we also include another Synopsys tool called Identify ME that allows you to debug your design. So I mentioned we start with design entry. And with design entry, we support HDL flow, where you can just use the text editor to create your own HDL files, or you can import files that you've already created and used in other designs, so you can reuse IP. Or you can use our SmartDesign tool, which is a graphical tool to stitch blocks together. We also support an embedded design flow. So if you have a soft processor, you can stitch blocks together that you can get from our IP catalog to create a processor system very quickly. For HDL, we support either VHDL 93 or VHDL 2008. We support Verilog 2001, and we also support System Verilog. And the entire Libero design flow supports mixed languages. So you can have VHDL and Verilog blocks in your design. You can bring them into your project. You can simulate them and synthesize them and so on. Another design entry method we have is our graphical tool that's called SmartDesign. The SmartDesign allows you to stitch together blocks of different types. It opens in a canvas, you bring the blocks in, and then you can make your connections. You can bring in HDL modules that have parameters or generics, and you can create a parameterized block. So when you bring it into the canvas, if you double click, you can open up a little dialog box that would let you change the parameters, so you could have different parameters for different instances of blocks if you want to do that. The output of SmartDesign is a component that's either in Verilog or VHDL that matches your project settings. Now, if you've used Libero SoC in the past, you're familiar with SmartDesign. It's a tool that's been around for a number of years now, but we made some exciting changes in Libero SoC PolarFire in the area of SmartDesign. One of the things that we did is we've improved the canvas. Now all of the components appear in columns, and all the nets are routed in this space between the columns. It gives us more, we have a more efficient placement and routing algorithm that we use for displaying things. We have new highlighting for nets and ports and other components within the design. The overall result is that you have a canvas that looks much cleaner. It's also much more responsive than previously. Here is an example of a RISC-V design that was done in SmartDesign. So you can see the components that are lined up in columns with all the routing in between. Now I mentioned RISC-V. So RISC-V, you may have heard about it. It's a new free and open instruction set architecture that was developed by UC Berkeley. And it's designed for simplicity. It's less than 50 instructions to run Linux, and also longevity. So there are standardized instructions that are fixed. That means if there's a new version of a RISC-V core that's available, your old design and your old code is going to still run. There's a RISC-V Foundation that's set up to protect the instruction set architecture and also foster adoption. And Microsemi is one of the charter members of the RISC-V Foundation. Now, the key thing with RISC-V is it's not an open source processor. It's an instruction set architecture. So even though there will be some open source implementations, one thing it gives you is the ability to innovate. And there's ways you could add your own instructions to RISC-V to have your own customized processor in your system. In Libero SoC, we have various different tabs that display information. One of the tabs is the Design Hierarchy tab. And the Design Hierarchy tab shows all of the source files in your design and builds up the hierarchy. In Libero SoC PolarFire, we've made some changes here too that improves the overall responsiveness of the system. We've changed to an on-demand hierarchy. So rather than rebuilding the hierarchy anytime there's a design change, we mark the hierarchy out of date. You can rebuild it as a user just by clicking the Build Hierarchy button at any time in the flow, or it's automatically rebuilt if you launch any of the tools that use the design, like synthesis or simulation. We've added some additional nodes. There's a user HDL source files node that shows all of the user HDL that's in your design. And we have a components node that shows any of the components that were created, perhaps components from the IP catalog that were configured, or they might be components that were created from other SmartDesign blocks that are being used hierarchically. So they all show up in one place. You don't have to sort through the hierarchy to find either your own user HDL or various different components that are used in the design. Once you've entered your design and you get to the verification stage, this is where you would use the ModelSim Pro ME simulator. The ModelSim Pro ME simulator is a Microsemi edition of the standard ModelSim Pro simulator from Mentor Graphics. It's limited to simulating only with Microsemi FPGAs, but it gives you support for mixed language designs, Verilog, VHDL, and system Verilog. And it allows you to verify your design at multiple stages. The design entry stage, where you're doing RTL simulation, gate level after synthesis, and timing simulation after layout, where you could take the netlist as well as the SDF file that's exported from the layout tool and do a timing verification to make sure you're meeting your timing objectives. We have some other changes in the area of simulation specifically for PolarFire in Libero SoC PolarFire. You can simulate the transceiver PMAs in the picosecond time domain for all the data rates, which is nice. Being able to use picoseconds means that your simulation is going to run much faster than if you had to go to a different resolution like femtoseconds. We've introduced a new bus functional model for simulating the PCI Express. The bus functional model has commands that allow you to emulate data that's transferred between the PCI Express block and the fabric across the AXI4 bus interface. Now here, with the bus functional model, the physical layer is not actually implemented. The intent of the bus functional model is to allow you to verify the interface between the physical media attachment and the FPGA logic, and allows you to run the simulation much faster. So that's the recommended method to simulate PCI Express designs very quickly. But an alternative method would be to use a third-party verification IP model for PCI Express. And in that case, you would have a register transfer model of the PCI Express, and the entire path could be simulated. That's something that you could work with a third-party vendor, get the verification IP, bring it into your Libero project, and then do a full simulation if you wanted to. Some other changes for PCIe simulation: we've updated the model to work correctly with the reset, the per RST signal for the ES silicon. And we also support the Mentor VOpt simulation, which reduces the simulation runtime. Early in the broadcast, I mentioned the design flow and the constraint step after we've completed design entry. So Libero SoC PolarFire includes something called the Constraint Manager, which has different tabs that allow you to go in and create constraints that can be used to constrain your IOs for layout, do floor planning, or create timing constraints, and then you can specify which tool should be using these different constraints. For the IOs and the floor planning, those would be for place and route. For timing constraints, we can create timing constraints for synthesis, for place and route, and for timing verification. And we could have the same constraint file that we use for everything, or we could have different constraint files and we could use them with different tools. So you could have one set of constraints you might want to use for synthesis, perhaps another set of constraints that you use for layout, maybe even a third set of constraints that you would use when you're doing your timing verification. That would allow you to perhaps over-constrain at synthesis, over-constrain at layout a little bit, but then have the exact constraints you're trying to meet when you do your timing analysis so you can see exactly where your margin is. We can automatically derive timing constraints for certain known blocks, like oscillators and PLLs that are in the PolarFire silicon. We can also cross-probe between some of the different tools, like the SmartTime static timing analysis tool and the chip planner floor planning tool. And we can also cross-probe between the static timing analysis tool and the graphical timing editor that we can access from the timing tab. Libero SoC PolarFire includes the Synopsys Simplify Pro ME tool for doing simulation. So here we're going to take our RTL and we're going to map that into a netlist that targets PolarFire. And you have some various other tools that are available to you inside of Simplify Pro ME. You can use the HDL Analyst tool set to see a schematic of the RTL, to see a schematic of the map design, and you can also see state diagrams, which can be useful when you're debugging, particularly if you have used things like one-hot encoding. It makes it a lot more clear to see exactly which bit represents different states. And Simplify Pro ME supports IEEE 1735 encrypted blocks. Some of the newer features that are available in the latest version of Simplify Pro ME that's in Libero SoC PolarFire 2.0 include ROM inferencing. So you can write case statements to describe a ROM. You can synthesize that and target the PolarFire device. And it will be implemented using a RAM block that will be automatically initialized at power up. You can infer RAM blocks that have byte write enables. We have the automatic generation of compile points. So compile points are RTL partitions in the design. And the synthesis tool treats each compile point as a block. The idea with compile points is that you'll go through and you'll initially synthesize your design, but then if you were to go back and make some changes, you'll only resynthesize blocks that were changed, and anything that's defined as a compile point that hasn't changed won't change again. The advantage of that is it works better in an incremental design flow because your netlist doesn't change very much, and you can go back and we can use our incremental layout. It also lends itself well to a team application. If you have various team members that are working on different blocks, if you define different compile points, then you don't have all the blocks being resynthesized all the time. Some other features, PolarFire devices include a math block for DSP functions, and the math block has a small coefficient ROM that's 16 by 8. You can automatically infer that coefficient ROM when you're writing RTL. And for the math block has built-in registers, and so we have register absorption. If you write a description where you have registers that are outside the description of doing your mathematical functions, the synthesis tool can automatically pull those registers into the math block and use the registers that are in the math block and save the other registers that are in the FPGA fabric for other logic. Other tools that are included with Libero SoC PolarFire include a netlist viewer that gives you a graphical representation of your netlist at various different stages in the design. So you can see the RTL netlist, post-synthesis netlist, and the post-compile netlist as you're going through, and you can cross-probe with various different tools. So if you're doing analysis, sometimes being able to see the actual netlist along with some of the other tools, perhaps to see delay information, can be really useful. So here's a look at the RTL netlist viewer. You open the Netlist viewer and you say you want to see the RTL netlist. It'll just show you a schematic of your RTL. If you click on a block, you can cross probe into the HDL code and you can open up and see the HDL code. Now this can be useful to make sure that when you wrote your description that it actually implemented the kind of logic that you had in mind. After you've synthesized, you can open the post-synthesis hierarchical view and you can see the kind of blocks that were used. So for example, if I was writing a description of a FIR filter and trying to use the math blocks, in this view I might just see symbols indicating additions and multiplications. In the next view I could see these big boxes might be the math blocks, and I could make sure that the math block looked like it got used, and I could particularly drill in and see, did the registers in the math block get used and things like that. Finally, we have our post-compile flattened netlist view. So this is the netlist that we're actually going to route. This netlist may have some changes from the RTL netlist. For example, we might have used some of the registers that are available in the I/O. So that will be reflected in this post-compile flattened netlist view. And this is the netlist that you can look at and cross-probe with the static timing analysis tool to really understand your timing. And if you're not meeting your timing objectives on certain paths, you can see the exact logic that's in the path. Another thing you can open is what we call the cone view. The cone view lets you open a blank canvas. And then from there, you can sort through the design and you can drag pieces into the cone view so you can sort of build up a view on your own. This might let you see critical paths that are displayed over multiple pages all on a single page, so it makes it easier to understand what it is that you're looking at. We have an I/O editor, and in Libero SoC PolarFire we've made some changes to the I/O editor, particularly in the area of the transceivers, to make it easier for you to implement your designs and place the transceivers, the reference clocks, and the PLLs and so on. So you'll see a schematic view that will show a representation of your transceivers, your reference clocks, your PLLs that are being used in the design. And then we have a physical view over here on the right that shows the different transceiver quads, the available reference clocks and PLLs, and you can drag and drop to make your assignments. So you kind of understand where you're putting things, which resources are available to you for those different quads. And when you make the connections, they'll be highlighted. You'll be able to see blocks in the schematic highlighted as well as blocks in the physical view. And we do design rule checks. So if everything is okay, you'll see little green lines showing all of your connections. I mentioned we do design rule checks. So if you try to make a placement that's illegal, you'll see red arrows that indicate that connection's not legal, and you'll also see messages down in the log window that will indicate these design rule check errors. So the tool won't let you make connections that aren't legal. We have a floor planning tool. It's called Chip Planner. Chip Planner will let you see the entire representation of the entire die. So you'll see where all the logic elements are, math blocks, RAM blocks, and so on. Chip Planner is kind of an interesting tool just to open and become familiar with the architecture. You can look at it, you can run layout, you can open up, you can see where all the cells were placed. But you can also use Chip Planner to do floor planning. And you can restrict the placer to put certain blocks in certain areas of the die. So if you want logic to go somewhere, maybe you're working in a team environment, you can carve out an area of the die that you don't want any logic put in because you're going to put another block in there later on that somebody else is working on, but you want to see where you are with everything else. You can do some floor planning here. And then you can cross-probe with the SmartTime timing analysis tool after you've run layout. So if you find that you have some timing violations, you can open the chip planner tool and you can highlight the exact path, and you can see where the logic was placed. Maybe the logic was kind of spread out, maybe doing a little bit of floor planning and trying to restrict that placer to keep the logic closer together could help you meet your timing objectives. So using this tool, but the other tools can really help you out and accelerate your design and debug time. You can use the chip planner tool to do floor planning. You can make all of your constraints, your physical constraints, your timing constraints, and so on. And then we get to the point where we push the button and we let the tool do all the place and route. So that's going to take all the cells in our netlist. It's going to put them somewhere on the die. It's going to make all of the routing interconnects. Now we have some options that we can use for layout. We start out with timing-driven layout. That's checked by default. So that will use timing constraints that you've created, and it will use those to guide the placer and the router to try to meet your timing objectives. If you don't have timing constraints, or if you just want to do a quick and dirty layout, you can just uncheck timing-driven, and you can just let the placer place the logic and make all the interconnects. But timing-driven tells the tool what your objectives are, so it gives it more information. We also, by default, check something called repair minimum delay violations, which tries to repair any hold violations that might be encountered as you're going through and we're running layout. You have some other options if power is a concern. And we have very low power with these devices, but we have a layout option that tries to minimize the amount of power that's consumed in the nets, and that can help you reduce your power consumption by maybe 15% or so. So you can check power driven if power is a concern. We have a new feature that's just been introduced in Libero SoC PolarFire 2.0 that's called driver replication. This enables an algorithm that replicates critical net drivers to try to reduce timing violations. Now, of course, if you do this, you're going to split one net into multiple nets, so there's going to be new names. So there's a report that comes out that tells you what all the new names are, and you could go back and you could modify the names in any of your timing constraint files so that when you go back and do your timing analysis, you make sure you're looking at the proper nets. Then we have a couple of other more advanced options that you can use, and you might use them if you're having issues meeting timing. We have something called high effort layout that spends more time and tries to do more optimization to try to give you a little bit better performance. We have an incremental layout. So if you go run through layout, you need to make a small change, maybe change a few pin assignments, or maybe a small change to the logic, and you've maybe just changed one compile point when you resynthesize. You can use the incremental layout option to lock the placement of any blocks that haven't changed and just incrementally do place and route. Runs faster, and it holds the timing for anything that hasn't changed. And then finally, we have a multiple pass option where you can go through and direct the timer to run layout up to 25 times. We'll start with a different seed index every time. So that's another method that you can use to potentially improve your timing if you have timing violations. Once you've completed layout, you move on to the timing analysis step. And we have a static timing analysis that's called SmartTime. SmartTime supports a wide range of timing constraints. You have an option to create multiple scenarios, so you could use different timing constraints for different operating conditions if you wanted to. You can graphically display different path sets and see if you're meeting your timing or not. It's displayed up at the top: required time, arrival time, and slack. And you can even see a graphical representation of the path that's being displayed. And then, as I mentioned earlier, you can also cross-probe this to chip planner so you can see exactly where all these cells are placed on the die. You can also generate timing reports from here that you could save, sit down and study and get more additional information if you needed to, if you were not meeting your timing objectives. We have another tool that's called Smart Power. And Smart Power allows you to determine the power consumption of your design. It will display your static and dynamic power. And it allows you to create different scenarios. So a scenario might be different operating conditions, such as stopping the clock, taking advantage of low power mode called flash freeze, maybe turning off the supply voltage for a while. And you can define these different conditions to run the device, and then you can see your power, the total power, the static, the dynamic power. We also give you a breakdown of the power, how much power is used in nets, how much power is used in gates, and so on. The advantage of seeing that breakout is it gives you a first pass to understand where the power is being consumed. And if you're over the power budget, then you can decide, how do I want to try to attack that? For example, if we saw a big slice here in the power consumed in the nets, well, that's what power-driven layout tries to reduce. If you saw something in the memories, we have the ability to optimize memories that are inferred through synthesis either for power or for speed. So if you verified that, yes, I have a comfortable timing margin on my memory operations, but my memory is using a lot of power, perhaps going back and resynthesizing and using an option to give me a more power efficient memory might reduce my power consumption. So once I know where the power is being consumed, then I can go and develop some strategies to improve that. We have other tabs that even allow us on the analysis tab, for example, we can drill all the way down through the hierarchy. So you can see where the power is being consumed throughout the design hierarchy. And we also work with simulation files. You can run a post layout simulation and generate a VCD file. You can import that into the Smart Power tool to get a more accurate estimate of what your power consumption is. You can even get what we call a cycle accurate power report that will show you the power consumption cycle by cycle. So you can refer that back to your test bench, and you can see if there's certain operations in your design that when those happen, or at certain points in the design, suddenly I get a big power spike. So this tool is really useful if power is a concern, to help you understand what the power consumption is and zero in on where the power is being consumed if you're over your power budget. The PolarFire devices have RAM blocks in the FPGA fabric, and these blocks can be initialized at power up. It's a little bit different than what we've done with some of our other families. It's kind of a new feature. We can store configuration data for the memories, these RAM blocks, in non-volatile memory. We have two types of non-volatile memory in PolarFire. We have something called the microprom. We have something called the SNVM, this secure NVM, or we could store data in an off-chip SPI connected to the device, and at power up we can get that data and we can initialize these RAMs. So we have a tab within Libero that's called the Design, Memory, and Initialization. And you can go through, after you've run layout, before you generate your programming file, you can go into this tab and you can specify the initialization data for your different memories. And then that data those memories will be initialized using that initialization data when the device powers up. Another option is that you can initialize the RAMs to 0 if you want to. So if you wanted the RAM to come up in a known state, you could initialize everything to 0 and you'd know every location would be 0 rather than just coming up in some random state. So this is a look at the Design Initialization tab. You would launch that from the Design Flow tab by clicking on Configure Design, Initialization Data, and Memories. And you have 4 tabs here. Design Initialization. This is where we specify the different stages for initialization. Now, 2 of these stages are pretty much fixed and they come out of the secure non-volatile memory. The third one, for initializing memories, in the design, you have the choice of initializing them from the microprom, the SNVM, or from external SPI. And then from there you have tabs for the microprom where you can create partitions where you're storing data, secure non-volatile memory, and the SPI flash. And then you'll see a tab that shows all of your fabric RAMs, and you can bring in your initialization data. So for example, on this slide, we're showing some RTL code that uses a case statement to infer a ROM. And after I go through and synthesize this, go through all my layout steps and everything, and I get to where I'm going to initialize the memory, if I go to the Fabric RAMs tab, I would see the RAM that's implemented to work as a ROM, and I would go off and I could load the design configuration data, bring in this memory file that I want to use, and on the design initialization tab, I can specify where I want that initialization data to be stored, either in the microprom, the SNVM, or an external SPI flash, and we can program this external SPI flash from Libero SoC PolarFire. So we've run layout, we've verified timing, we've optionally verified power, we've set up all of our initialization. Next thing we're going to do is we're going to create our bit stream, and we're going to program. And we provide programming tools that allow you to take your board, connect to it with the programmer, and program. You can program PolarFire devices through the JTAG interface or through a SPI programming interface. And we have various different programming modes that allow you to do updates in the field and so on. Before you generate your programming file, you can specify custom security. So you can put in your own user keys if you want to. You can put in a silicon signature. You can put in a design version, which is one of our security features. By putting a design version into your bitstream, you can prevent old bitstreams from being used. You can specify what is the oldest bitstream that can be used. So if somebody gets a hold of an old bitstream and you've done some kind of field update, they won't be able to use it. You can program the security settings, the fabric, and the secure non-volatile memory all in one shot, or you can program them separately if you want to. And we also support our industry-leading secure production programming solution, which allows you to take blank devices, drop ship them to a contract manufacturer, and program even the keys in an environment that's completely concealed. So even though you're in an untrusted environment, keys are never exposed, and you can confirm the correct programming file was used, the correct number of devices was used, prevents overbuilding, prevents cloning, and a number of other threats that customers face when they go off to contract manufacturer. After programming, you can have your board, plug it in, hopefully everything works, but sometimes it doesn't. And if it doesn't, you need to start digging in and doing some debugging. And here we've got some tools to help you out as well. We have a tool that's called SmartDebug. It's a Microsemi tool that really helps you debug your device and get it up and running quickly by taking advantage of some features that are built into the silicon in PolarFire. The great thing about this is that these features, the features that are built in for debug in PolarFire don't require any FPGA resource usage. So you can examine internal points in the design on the fly without having to go back and reprogram the device. Another alternative for debugging is to use the Synopsys tool Identify-ME. Identify-ME is an RTL debug tool that allows you to identify logic that you want to be able to observe when you're in your debug state prior to synthesis. And it adds additional logic that allows you to set trigger points, and you can think of it as having a little built-in logic analyzer so that you can set trigger conditions and then you can view data that's inside the device. So SmartDebug takes advantage of logic that's added to the basic logic that's available as a user. So in PolarFire, all the logic elements consist of a 4-input lookup table with a D flip-flop. Over the top of that, we've added logic that allows us to bring out some of these signals that we can take to one of two pins that you can probe. So logic is organized in what we call a cluster. And within a cluster, we have groups that we can bring signals out. So we can bring the output of any flip-flop to one of two pins. So we can observe what's going on to internal signals by connecting to a scope or a logic analyzer. And you can change the signal that you're looking at, the signal that's assigned to these probe A or probe B channels, without having to rerun layout or recompile or do anything. All you need to do is select a different signal to observe. So it gives you a way to see what's going on internally if the IOs aren't behaving properly. So SmartDebug, when you launch it, you see a window that looks something like this, and there's a number of different tabs that will show up, little buttons that will allow you to open different tools. In the FPGA debug button, you can use what we call the live probes or active probes. So live probes are the two channels that let you bring out the output of any flip-flop to one of those two pins. Active probes let you take a snapshot of all the flip-flops in the design so you can see what's going on. We have the ability to take a snapshot of the memory. We can even change memory contents. And then we also have something that's called probe insertion. Probe insertion allows you to route signals to pins. Probe insertion actually causes you to do an incremental place and route. And then we have a transceiver lane debug. So I'll show you a few of these in a bit as we go along here. SmartDebug is available. It can be launched from Libero. It can be used in a standalone mode. Now the standalone mode is perfect if you're in an environment where you're in a lab and you want to debug the design, but you don't want the entire design project available. You can export a debug file, you can have the board, you can run standalone SmartDebug, and you don't expose all of the design. We also have a demo mode, which is nice for people that just come up to speed with what SmartDebug looks like and some of the capabilities without having to use a board. Okay. So here's the idea with Live Probe. We have two channels. We have these internal flip-flops. We can assign any flip-flop to one of those two channels, and we can observe it on a scope or a logic analyzer. And we can go back and we can change the signals that are connected to these probe points without having to do anything more than select a signal and say assign it to channel A or assign it to channel B. Active probe lets you see a snapshot of, see the whole design if you wanted to. You can go and you can read the active probes. It will show you the state of the signals. You can go in and you can write these too. We can asynchronously write them. The issue here, if you asynchronously write them, is it doesn't stop the clock. So if you go back and read again, some of the asynchronous writes you do might get overwritten if the clock is running again. But it lets you take a snapshot of what's going on internally. Probe insertion gives you the ability to add signals and route them out to pins. And they could be pins that are unused, or they could be pins that were previously used. Probe insertion requires the design to be routed again. So we do an incremental route. The idea is I normally had a connection from 1 to 3 over here. I still want that connection, but I'd like to see what's going on with 1, so I can route it out. So probe insertion has an advantage over live debug because you could bring out more than 2 signals at a time. But anytime you make a change with probe insertion, you have to go back and you have to run layout, and then you have to program the device. With live probe, all you need to do is select a signal and assign it to channel A or channel B. And probe insertion relies on the layout engine, so it's not available in the standalone version of SmartDebug. We have a tab that lets you look at the fabric SRAM blocks. So you can see the SRAM blocks. You can read the blocks. You can even write new data in there if you wanted to. Secure non-volatile memory is a small 56K byte block of non-volatile memory that can use plain text that's either non-authenticated or authenticated, or it could use encrypted text. And you can observe the data that's in the SNDM. And then finally, we have built into SmartDebug tools that let you debug the SerDes blocks. The SerDes blocks themselves have some built-in hardware in the physical media attachment layer. We can do PRBS 7, 9, 15, 23, and 31 tests. We also have some soft IP that's called SmartBERT that you can use with the transceivers that allows you to run various different pseudo-random bit streams and insert error. So you can insert errors and you can see logic. We have an error counter and so on. So you can display the lanes, you can see the status, and then you can inject errors if you want to, and you can see what the error rate is. We have a signal integrity tab that's available through many of the different transceiver tests, SmartBERT, the loopback modes, and so on. There are places where you have pull-down menus where you can change the transceiver emphasis, amplitude, the impedance, and so on. Once you've made these changes, you can go off and you can export that as a PDC file, or you could import a PDC file. So you have the ability to kind of fine-tune the transceivers, either the receive side or the transmit side. We have a tab that lets you specify different loopback modes for the different transceiver lanes. You can do near end, far end loopback, or no loopback at all if you want to. And then you have the ability to put static patterns through the lanes. You have a you can do a fixed pattern of alternating ones and zeros. You can have user-defined patterns. You have a max length pattern, which is an alternate of basically half the data is ones and half the data is zeros, and the width matches the width of the transceiver lane. Then we have the Eye Monitor tab. The Eye Monitor is a non-intrusive estimation of the eye monitor as you're running. So you're running data through the transceiver lane, and we estimate the horizontal and the vertical eye opening. So you can get an idea of what your eye diagram's looking like without having to have other expensive equipment. And then you can go back and make changes to the signal integrity options and take a look and see what the eye diagram looks like before you finalize everything with the transceiver. So those are all of the different tools that are included with SmartDebug. And then another alternative for debugging is to use Identify, which is a synopsis tool. It's included with Libero. You don't have to pay anything extra for it or anything. This is an RTL source level hardware debugger, which means you start using Identify prior to synthesis. You would implement your design. You would open synthesis and launch Identify, and in Identify you can specify signals that you want to be able to trigger on, and signals called breakpoints that are in the flow, either case statements or if statements that you want to be able to set a breakpoint on. And then you go through and you synthesize the design. Identify will add additional logic to your design, and then there's a piece that you use after you've programmed the device called the Identify Debugger that allows you to set your trigger conditions, much like you would with an oscilloscope, but it's all based on internal signals, and then you can shift the data out and you can view it in a waveform viewer. Finally, when everything is working, you met your timing objectives, you met your power objectives, and you're off to go into volume production. If you're using a contract manufacturer, you can take advantage of our Secure Production Programming Solution, or SPPS. SPPS works by having some hardware security modules on each side. One on the customer location side, where you have your design. Now you want to have a contract manufacturer make a certain number of devices for you. So you create what's called a job ticket that gets transmitted to the contract manufacturer, and the contract manufacturer is running their own HSM. They get the job ticket. They have Libero. Keys are securely injected into blank devices. and the devices are programmed. So we specify who can program the devices. It validates it's a valid Microsemi device before it's programmed, controls the exact number of devices that are programmed. And you get a certificate of confirmation later on, so you can confirm that the device was programmed with the correct bit stream and so on. So it eliminates a number of the security risks that are involved with going to a contract manufacturer when you give them all your design files and you're ready to be in volume production. No more cloning, no overbuilding, and so on. Finally, if you have a design that has an embedded processor, we have you covered there too. We have a tool that's called SoftConsole. It's based on the Eclipse IDE, and it lets you do your firmware development. SoftConsole is completely free, and it works for the RISC-V, which we have our own version that we're branding as My5. So you see this My-V here. My5 is the Microsemi branded version of RISC-V that's available. It also works for ARM processors. So any of our parts that have the Cortex M3, we have a soft Cortex M1. You can use SoftConsole to develop code for those. Runs on either Windows or Linux. Okay, and we have a number of example projects. We have some RTOSes for different designs and so on. So you can develop your code, download to the board using the same programmer that you use to program the device initially. So you don't need any extra hardware to access and debug your design running in a PolarFire device. Okay. So we can do our standard debugging. We support the breakpoints. You can look at memory locations and so on. And it works with the Flash Pro 5. It also works with a couple of other dongles as well, like this Imulex ARM USB Tiny H dongle. So I'm just about out of time, but I went over, gave you a quick introduction to PolarFire, went through the flow with PolarFire, Libero SoC PolarFire, and then we talked about some of the debug capabilities that are available. So why don't I just kind of stop at this point and see if maybe there's any questions we can answer in the last couple of minutes. If we don't get to answer your question, by the way, we will we'll send out answers.
Yes, thanks, Tim. Yes, there are quite a few questions. So I've kind of prioritized the ones that are more general, and the ones that are more user-specific we'll probably handle offline. But the first one is actually a question that I can respond to. You will receive a recording link to this session, plus a PDF of the slides will be sent out to anybody that registered for the session. So this was somebody that wanted to go back and review it again later. So definitely good material. Thank you. The second question is, does LiveProbe use dedicated pins, or can these be assigned to any pin?
They're dedicated pins, and you can specify when you create your project if you want to use the probes or not. So if you don't want to use the probes, then those would be available as user pins. Otherwise, there's two dedicated pins. When you look at the different pin assignments on the different packages that are available, you'll see a probe A and probe B.
Okay, sounds good. So this one is about the locking logic. If logic placement is locked within a user specified region, then is the routing associated with this logic also locked from one design iteration to the next?
I'm going to have to get a confirmation on that. On some of the earlier families, it was. I'm not sure on PolarFire, so we'll just take that one offline.
Okay. Can you go back to slide 33 if possible? Jump to there. There's a question about what's in the middle box in slide 33 image.
The middle box, the Flash Pro 5?
I guess it was, I just couldn't see the slides. So yeah, that's your program debug dongle, right?
Right, yeah, so here we have a PC where we have Libero installed, and we've created our programming file. And then on the right, we have one of the boards, a PolarFire board. And then we have a low-cost programmer. It's called Flash Pro 5. It connects via USB to the PC host, and it connects to the board through a 10-pin JTAG header. And that Flash Pro allows you to program the device, and then you can also use that if you're using SoftConsole to download code to your board if you have a design that uses a soft processor like a Cortex M1 or a RISC-V, and you can develop your code.
Okay. And then this other one is a good question. I don't think we have it, but it's a good point. Is there a comparison anywhere of what features are available for example, Igloo 2, SmartFusion 2 versus PolarFire? For example, like SmartDebug or SmartDebug, that sort of thing.
I don't know over off the top of my head, but we could put something together. We'll just take that one offline and put it together.
That's what I was thinking. But the major higher level tools that we've talked about apply to SmartFusion 2 and Igloo 2, but some of the features we talked about today are new additions for PolarFire. So correct, yeah, I think that's a very good point that we could get a comparison table going for that one.
Yeah, for example, SmartDebug is available for SmartFusion 2 and Igloo 2, but the Eye Monitor for the Transceiver Debug is not there. So there's more capability. There is a Transceiver Debug capability in SmartDebug, but there's more capability for PolarFire.
Okay, and let's see, are anti-cloning and overbuilding support available for the lower density CPLD replacement devices?
Well, we do have the ability to put security keys in those devices. And you can prevent overbuilding by taking a device that has a key programmed into it and giving an encrypted bit stream to your contract manufacturer. If you do that, when they take the bit stream, they won't be able to see the keys, and they'll only be able to program devices that have the key put in. So if you give them 50,000 parts and they try to buy another 10,000 parts, it won't have the key, they can't use your bit stream. So that does prevent overbuilding, but you don't get the report back, you know, to verification of things like you can with the SPPS. SPPS works for SmartFusion 2, Igloo 2, and in PolarFire because we have additional security features. So with those devices, both those families, you can drop ship a blank device and you can have everything programmed in, whereas with the CPLD replacements, you would have to have the key programmed in a trusted environment because somebody's going to know what the key is. Once you've done that, you can create an encrypted bit stream and give these devices. So there is a way to prevent overbuilding. It's not as elegant as it is for SmartFusion 2 or PolarFire.
Okay, thank you. And then one other one just to follow up on access to information. There was a question about accessing Libero user guides, etc. So those are available on either the Libero SoC PolarFire page, or if you're using SmartFusion 2 Igloo 2 on the Libero SoC Design Suite page, and that includes all of the documentation for Libero and for these individual sub-tools. And we can also post the recording of this webinar will be posted to those web pages in a couple of days as well. So I think, Tim, there's a lot of other very detailed questions that I think we can get back to users individually if you want to wrap it up.
Okay. Yeah, that sounds good. Why don't we wrap it up? So thank you for attending. We always appreciate you taking the time out to let us tell you about our great products. Next thing for you guys to do, if you're interested, go out to our website. We have more information on PolarFire SoC, or Libero SoC PolarFire, and you can also download it and get a free evaluation license so you can play around with some of these tools. You won't be able to program a board, but you can open SmartDebug in demo mode and so on, so you can become familiar with, even more familiar with all of these different tools that I went through quickly today. So again, thank you very much for your attention, and we hope to have you attend another seminar in the future.